This is Audiovisual Lecture 7, Part 1. Today we're going to go over weight and balance per the syllabus. The only change on that is going to be a reading selection from Chapter 9 in addition to what's on the syllabus for Chapter 4. Chapter 9 just has a lot more in-depth information on weight and balance, particularly the kinds of problems that we're going to have on the quiz and final exam, and the processes for working through those. So an email will go out outlining that reading material. The substance of what we're going to go over today is covered in Chapter 9 as well in the book. We'll go over a little bit of the theory and then go through some of the weight and balance performance problems. So the first part of this, weight, is fairly easy to grasp as a concept. Weight is what it is. If you weigh 100 pounds, then you weigh 100 pounds, and that's the force that you're exerting on the airplane once you step onto it. So weight, or gravity, being one of the four forces of flight, simply means that the greater the weight, the greater the pull that the Earth will have on the airplane, so the more force the airplane will have to overcome to maintain straight and level flight. So to put that more simply, weight adversely affects the performance of an airplane. The more that you push down on an airplane, the greater the angle of attack will have to be to maintain level flight. So the greater the drag will be, the lower the cruising speed will be, and generally the less performance will be available. There are some altitudes that an airplane can fly at a lower weight that it can't get to at a higher weight, simply because it can't overcome the force of gravity at that higher weight. To get as high as it's capable of flying based on its engine performance and the performance of the wing and so forth. So weight is just what it means. The greater the weight, the less the performance, because the more force of gravity the airplane has to overcome to maintain level flight. Now, what we're more concerned about in this lecture is the balance of the airplane. And this is a very practical consideration because a lot of times you can load an airplane easily within its gross weight, or the weight at which you can't legally take off above that weight, because the engineers have tested it and determined that that's the most weight that it's safe to carry in that airplane. But where you put that weight within the airplane is just as important. If you think of a boat, for instance, if you put all the heavy people in the very back of the boat, the front of the boat's going to be sticking up out of the water. So you have to distribute everything evenly to keep the airplane balanced. And this brings us to the first definition that we'll cover, which is that of the center of gravity. So this is the center of gravity is a point at which, if you suspended the airplane, let's say by a string, at that point it would be level about the longitudinal axis. So the longitudinal axis being from nose to tail. So think of if you've ever hung a model airplane from the ceiling or something. To get that model airplane level, you would have to attach the string to that model airplane's center of gravity. So, for instance, this airplane drawn on a piece of paper has a center of gravity that's also the center of gravity for the piece of paper. And if I hold it there, it's going to be level about the longitudinal axis. Now, if we change that center of gravity, it's going to be either nose heavy or tail heavy. So let's say that the total weight that this airplane can uphold is, let's say, 100 pounds of cargo. It's a real small airplane. It makes a big difference where we put that weight. If we distribute it to where it's within a certain range, because there has to be able, you have to be able to fly with just two people up front, or enough to be able to have some baggage in the back. So there has to be a little bit of a range. It's not always going to be perfect. But the point is to not have it too far forward or back of that range. And there are a couple of points that we can go over that as far as the characteristics of that. So if the weight is the further forward the weight in the airplane is, that's what's called a forward center of gravity, or a forward CG. And the further towards the tail the weight is, that's a more aft CG, or aft center of gravity. So, and like we said, there have to be some allowances for the weight in the airplane to not be perched exactly at the center of gravity, because it's a infinitely small point as far as the very point. And the more that you go outside that point, the more the weight has to be to one side or the other. It's a pivot. It's a theoretical pivot point. So there are allowances to go forward or aft of that central point, and the limits are determined by the engineers that come up with that for that particular airplane. But for performance, we have to bear in mind that there are certain characteristics of a forward or aft center of gravity. Let's say that there are more people and bags in the front of the airplane, so the center of gravity is more forward. With a forward center of gravity, you generally have increased stability, but less performance and heavier control forces. So think of if there are a lot of people forward, you have to pull back on the yoke or the control stick more, because the tail has to work harder to go down and pull up all those people that are in the front of the airplane. Because of this, you're going to be flying at a higher angle of attack, because to overcome the weight of the people in the front, so you load the airplane and it naturally wants to do this a little bit, so you're having to pull back on the tail like this and kind of fly through the air like that. So greater drag, which leads to less performance. But it does have increased stability because it has the center of gravity somewhat closer, the weight's closer to that center of gravity. The exact opposite is an aft forward CG is increased stability for that. An aft center of gravity, you're going to have less stability, lighter control forces, and more efficiency. Because the more that you put the weight towards the tail, the more that's relieving the pressure on the control stick, and the more the efficiency comes from there being less drag. But there's lower stability because as we've seen with stalls and spins and so forth, it's much harder to recover from a spin or a stall the further aft the CG is, because to break the stall, you have to lower the nose and lower the angle of attack, right? But if you have too much of an aft CG, the elevator isn't powerful enough to lower the center of gravity. So it becomes, if the CG is too far aft, you have an unrecoverable stall or spin, and you just kind of do this all the way to the ground. So that's one consideration that the engineers are coming up with when determining how far aft the center of gravity can be and still fly safely. So just to recap again those characteristics, for an aft CG you have lower stability, lighter control forces, and more efficiency. For a forward center of gravity you have increased stability but less performance and heavier control forces. Now to go over what we're really going to cover is how to load the airplane within these limits. So we have to calculate what the weight and distribution of the weight is to know if it falls within those limits. So there are three terms that we're going to be using to determine this, and one of course is weight, as we've determined, and this brings us to the example of the teeter-totter or the seesaw, however you grew up saying it. And it's the same. It's a classic example of leverage and how a 50-pound person can lift a 200-pound person based on where the weight is distributed and how that leverage is used. So we have weight, of course, and then we have what's called arm. Arm is the distance in inches from the center of gravity to the spot in the airplane where the weight is. So let's say the center of gravity is here. Arm is going to be the distance in inches from there to, let's say, a bag that we put back here. The engineers generally will give a plus to an aft CG and a minus to a forward CG, depending on how that affects it. So arm, just again, is that distance in inches from the center of gravity to what's called a reference datum line, but that's just a fancy way of saying a point in the airplane where you actually stick the weight. So think of where you sit on the teeter-totter as being the arm. The arm is that distance in inches from the center of the teeter-totter to where you are sitting on the plank. And then the third definition is moment. The moment is the arm times the weight, usually divided by 1,000. So the moment, strictly speaking, is just the arm multiplied by the weight. But for calculations to make it a little easier, we usually take that product, which is the moment, and divide it by 1,000 just to make it an easier number to work with. So just to show it to you on paper, so moment equals arm times weight. So those are the three definitions that we're going to work with here in a minute. Weight, arm, and moment. Now, a lot of aircraft performance charts will do some of these things for you, just to make it a little faster and easier to determine center of gravity. But what we're going to do is we're going to work through a practical problem in weight and balance just to show you how it's done, and also to show you how to do it on the quiz and the final exam, right? So this is going to be a basic version of it. What all this is building up to is when we go through performance over the next couple lectures, which are the last couple lectures really before the review, we're going to be going over various performance aspects of the airplane that give us the cruise speed and how much fuel we're burning and so forth. And that all figures into it because those determine how much fuel you're using, how the weight changes as you burn fuel, right? You don't, when you take off to when you land, the weight changes because the fuel that you had when you took off, some of it isn't there anymore. So your center of gravity changes even as you fly. So, but for right now, we're just going to go over calculating the weight and balance at a given specific moment. No pun intended. So, the example we're going to use, we're using performance data from a Cessna 172 fairly common trainer. We're going to be using the data for a 1981 or a P model. It changes from year to year because as you change radios and change equipment and paint and little doodads here and there, that all minutely changes the weight and it also changes the balance. Even if you use the same seat the next year, if you move it back by 3 inches, you've changed the balance of the airplane because you're moving the seat 3 inches further from the center of gravity or closer to the center of gravity and so forth. So the point is to use not only model-specific information, but aircraft-specific information. Anytime that an airplane is changed, let's say you change a radio or you take the wheel covers off of it, or you put a modification on it, the center of gravity has the weight of the airplane and the balance of the airplane has to be recomputed so that you know what the basic empty weight of the airplane is, such that as the airplane sits there on the pavement at the airport, you know what its exact weight and moment is for that specific airplane. And that's important to know because that's the first thing that we start with on the computation. Just for calculating purposes, should it come up, any unusable fuel and oil weight are calculated into the basic empty weight, so we don't have to calculate those separately. So in the airplane's manual, there's going to be usually a chart, a sample chart, just to kind of show you how it's laying it out for that, a sample loading problem, they're calling it. I've just kind of drawn one out here on paper. So we're going to tally up a couple different things. We're going to tally all the weight that we're putting on the airplane, including the airplane, and we're going to tally up the moment, which again is the arm times the weight, and these numbers are divided by 1,000. Again, just to make that an easier number to work with, so you don't have a whole bunch of zeros out here. So the basic empty weight of the airplane, they put it on scales like your bathroom scale and determined that it was 1,467 pounds and that the aft moment of that was 57.3, and that's again that product of the arm times the weight.